Good afternoon, everyone. My name is Zhiwei ZHANG. Today, I will be presenting our work on efficiently fine-tuning a large language model for the specific task of generating scalable vector graphics, code directly from text descriptions. This project was part of our participation in the Joining with LLMs Kaggle competition. Well, let's start with a quick overview of what we will cover. First, I will briefly introduce the Kaggle competition itself, and then we will dive into our methodology, detailing the model techniques and the data we used. Following that, I will present our results, including our final ranking and some examples. Finally, we will discuss the key factors behind our success, acknowledge limitations, and conclude. Moving into the first section, the competition overview. The primary goal of the Drawing with LLMs competition was challenging to develop models capable of generating valid and visually accurate SVG code based solely on a natural language prompt. This involves bridging language understanding with precise code generation. Notably, it was the first Kaggle competition requiring submission as reusable model packages, testing not just model performance but also software engineering practices. To succeed in this competition, we had to adhere to several specific technical requirements and constraints. For example, the SVG constraints and submission requirements. And the most important thing is the evaluation pipeline. The pipeline itself involves multiple steps, including validation, conversion to PNG, VQ assessment, OCR checks, and aesthetic scoring. Now, how was performance accurately measured? The core metric was the SVG image fidelity score. This score cleverly combined two main components. First, a VQ or visual question answering score, which measured how faithfully the generated image represented the text prompt, using the polygamma model and penalizing unwanted text found via OCR. Second, an aesthetic score, assessing visual quality using clip. This was combined using a hermetic mean with beta set to 2, which heavily prioritized the VQA score, meaning accuracy and faithfulness to the prompt were valued more than just aesthetics. Well, having understood the competition, let's move on to section 2, our methodology. Here is a high-level overview of our approach. Our core strategy centered on fine-tuning the Qianwen 3 4B model, chosen for its balance of capacity and size. To do this efficiently under Kaggle's resource constraints, we leverage the Ansource library for speed and memory optimization, combined with LoRa, a parameter-efficient fine-tuning technique. We combine this setup using a quality filtered static dataset. A crucial part of our strategy was selecting the RAD-based model. We chose Qianwen 3 4B for several key reasons. Its 4 billion parameter size offered a good compromise between capability and the computational cost feasible on a single Kaggle T4 GPU. Importantly, its pre-training included a significant amount of code, making it inherently well-suited for code generation tasks like SVG. It also demonstrates strong instruction following abilities and was reliably available on Kaggle. To make fine-tuning feasible and effective on the available hardware, we leveraged two key technologies. First, Ansource, a library designed to accelerate LLM training through optimized kernels and memory management, giving us significant speed-ups and VRAM reduction. Second, LoRa, or low-rank adaptation. This path technique allowed us to adapt the model by training only a small number of adapter parameters while keeping the base model frozen. We used a relatively high rank of 128 for LoRa to capture more task-specific nuances. Of course, the model needs data to learn, of course, the model needs data to learn. We use the sample training data provided by Kaggle, consisting of about 1,000 prompts SVG pairs generated by GPT-4o and filtered for quality using stick leap scores. To get the model efficiently, we formatted this data using the alpaca instruction following template. Our training configuration involved a small batch size with gradient accumulation, a learning rate, the memory efficient XAM 8-bit optimizer, and run for 300 steps. Crucially, thanks to a Sleuth and LoRa, the entire fine-tuning process completed in approximately 2 hours on the TS4 GPU, as shown by the converging loss curve. Now, let's look at the results of this methodology in section 3. Our efforts accumulated in a strong performance on the public leaderboard. By now, we achieved a final score of 0.646, which placed us 50th out of 1276 participants. This result secures us a silver medal, positioning our solution within the top 4% of the competition and validating the effectiveness of our approach. Beyond the quantitative score, let's look at some qualitative examples of SVGs our model generated. As you can see here from 4 prompts like lighthouse looking the ocean, black and red checkered pants, and a snowy plain. The model successfully captures the main objects and scene compositions. It demonstrates an ability to interpret both concrete and abstract concepts, utilize SVG primitives appropriately, and crucially, avoided generating text, which help us avoid the OCR penalty. While moving into our analysis in section 4, what were the key factors contributing to this success? We believe it was a combination of things: the strong foundation provided by Tianwen model code capabilities, the expressiveness gained from using LoRa with a higher rank, the crucial efficiency boost from and source enabling rapid iteration on the T4, clear task guidance via the instruction format, and using quality field data. While we achieved good results, it's important to acknowledge the limitations and the potential areas for future improvement. Our model's performance is inherently tied to the diversity of the synthetic training data. Generating highly complex or novel geometric structures remains challenging, and the process is a single pass without refinement. Looking ahead, future work could involve exploring larger models, augmenting the training data with human-authored examples or more diverse synthetic ones, experimenting with advanced path methods like LoRa, or implementing post-processing steps to refine the generated SVG code. Well, to conclude, our project successfully demonstrated that fine-tuning a moderately sized LLM like Tianwen 3.4b, enhanced by efficient tools like LoRa, is a potent and resource-efficient strategy for specialized code-generating tasks like Text-to-SVG. Our achievements of a silver model, for example, the rank 50 in this competitive Kaggle challenge, this claim. This methodology provides a viable pathway for developing high performance models, especially under limited computation budgets. Well, this brings me to the end of my presentation. Thank you very much for your attention.